Good afternoon, folks. I'm Atri. This is Rohit. We are from Uber, and we're going to talk about how we migrated from Elasticsearch to Pinot for mobile app crashes. So I'll set some context around what the main problem was, and then Rohit will go into depth of how we executed this and what were the wins and learnings that we got out of the entire exercise. Without getting into too many details first, a very simplistic use case. So at Uber, we actively track our app crashes and bug reports. So people do tend to file a lot of bugs or issues that they see with our family of apps. And then we have crashes happening at on different platforms, different versions with different binaries, different app status. In some scenarios, we roll out a new feature and it suddenly starts leading to incremental crashes on areas that we might not have thought of. So we have an automated pipeline that tracks these crashes, puts them, collects investigated data such as stack traces and whatnot, and then puts them into a pipeline where some machine learning models run on top of it, and we can basically identify and tag certain crash types to roll out. So this kind of debugging or health analytics becomes much easier. So we have an internal code name for the search service, but we'll stick to that. So this historically has been on Elasticsearch because there were analytics performed there, and there was also a significant text search use case, as we can imagine. And recently, there was this effort as a part of the Elasticsearch deprecation program that is currently going on at Uber. We decided to move away from this stack and move to Pinot. And one thing that we did want to do was not break feature parity and also get more wins out of it. So it should not be something that we're doing only from because we have to do it or from a mandate perspective, but we wanted to show real wins out of the Pinot ecosystem. And we did get significant wins, as we'll see today. So yeah, that reinforced the fact that Pinot is a great system at what it does. And many a times, people tend to misuse Elasticsearch for analytical capabilities where it should not be. And it's also a testament to the fact that Pinot has come a long way in building new types of indexes such as text search that can augment its capabilities and allow people to do more than just simple time series. With that, I'll hand it over to Rohit to go into specific details, and then we'll take over questions.
So thanks, Atri. Yeah, just to add to what Atri was saying. So if you look at this dashboard, so starting from the first row, you see there are two graphs about total sessions and total users. So this is basically giving us total unique sessions and total unique users at the day level granularity. Similarly, the third one is showing how many total fatals or the crashes were there on a mobile app. So this is just a view of one mobile app for one operating system and one of the version and last 7 days of data. We then combine these metrics and then find fatal free rate, which is basically an indication of how healthy your application is. So in general, we try to have it as close to 100 as possible. If you see, there's a very small line which is under 99%, and then it gradually goes to 100%. That's mostly because we also have a cycle of beta app rollouts, wherein a beta app will have some experimental features, and then we want to track how healthy is it. And it only becomes eligible for a release for a wider audience once it has passed a certain threshold of fatal free rate. Yeah, and then there's an adoption rate graph. One line is going down, that's the older version phasing out. The other line is going up, that's the newer version coming up. And then finally, we also give how many, like, per crash module or per module of an application, which is the most crash causing one. So yeah, this is like a very snapshot view of it. We also provide in-depth crash level analysis. So each crash is also clustered together. So all the similar crashes will form a cluster, and that then we provide analytics around that cluster. So for example, let's say we launched a new feature on a particular screen, we started seeing a lot of crashes. So all those crashes for that particular screen are grouped together. Then there are a bunch of ecosystem services built around it. So for example, any new feature enabled via an experiment, as soon as we start seeing crash spikes for that, we'll directly assign it to the last person who made the code commit. And then there's whole ticketing and alerting system around it, and then people can work on it, and then it gets closed. So yeah, this was a very brief overview about it. Some similar enterprise solutions are like Bugsnag, Firebase, Sentry, etc. And we also do the similar kind of analytics for backend services log as well. So just like there are crashes in your mobile application, there can be backend service generating error logs. So we provide a bunch of analytics and clustering around them as well. So just to briefly talk about the numbers, so the session counts that I was showing, that is derived from the analytic events, and the scale of analytic events can go up to 200 or 300,000 per second. So you can imagine it's a lot of data we need to process if you want to store and provide unique session counts around it. Similarly, crash events can be double-digit number. It can be from a few thousand to 15 or 20,000 in cases if we are seeing some spikes in crashes. Payload size again varies a lot, few KBs to hundreds of KBs, and that's mostly because your crashes can have a lot of metadata around it. It can have network logs, analytic logs, uh, and then any other crash payload around it. For example, the experiment payload, what all experiment parameters were activated during that time. And finally, the data footprint on Elasticsearch was around 150 to 160 terabytes. This is a very huge number just for the analytics purpose if you are trying to solve for. So to summarize, I'll say a lot of cost was from the ELK setup that we had. And it was not just the cost aspect of it. There were situations where if we have spikes in spikes in crash rates, then Elasticsearch would lag in terms of ingestion. So then we'll have larger ingestion lag. Because it's a larger ingestion lag, we'll be slow in identifying any issues happening. And given this tool has to be very near real time, this is a huge miss if Elasticsearch is not performing well. So this gave us the natural reason to move to something much better. And in our case, it was Pinot. It's a very high-level summarized model. So if you see previously, the Kafka events are directly going to your ELK setup. It is now being replaced by a very simplistic structure because Pinot has direct Kafka consumers and it can directly consume from Kafka topics. There are some more changes needed. For example, your Elasticsearch can pretty much store any kind of structure of document. In Pinot, it's slightly more schema-driven. So that is where we need some kind of transformation wherein we use Flink jobs. There's also a branch which is missing over here. That's the offline data that we also push to Pinot. And the offline data is being pushed because we are going to create hybrid tables over there, which will have the real time and the offline part. For visualization, we rely on Grafana and some of the internal tools. So that's how we were also able to get away from Kibana. Yeah. Looking at the existing cluster setup for Pinot, so we have an active setup. There are 2 regions. So this is the summary of one region. So we have around 6 real-time servers, 8 offline servers, and 2 brokers for querying. I hope the previous sessions gave you an idea of servers and brokers, but in case you have any questions, just let us know. So to summarize and comparing it with the ELK infra, so in ELK, we were using around 22,000 cores of CPU, but here we are doing it with just 2,000 cores of CPU. I'll go to the win section wherein I'll give down the cost benefits that we have with Pinot. But this is just to highlight that how very less infra footprint can solve the same use cases which are being solved from Elasticsearch. And also to state that it's not a problem with Elasticsearch, but I think Elasticsearch has so many features at its disposal that we build so many things in very short amount of time. And then when it comes times for maintenance or scaling up, we just add more hardware to it, and that's what adds to the cost. In Pinot, we step back. We try to understand the use case as well before even putting any infrastructure numbers in place. Yeah, so let's look at the use cases being served by Pinot one by one. So yeah, this is the use case about counting unique sessions, users, devices at Uber scale. As mentioned before, it's like 300,000 analytic events coming at once. First challenge is consuming so many events in such a small amount of time. Either you need a very high scale throughput real-time processing system, or if you solve that also, then you need some persistence which can store these many events in your storage. So what we did was we tried to understand the use case. The use case was to be near real-time. It wasn't to be super fine. So that means that we do not want point level analytics, but it can be fine if we provide some roll-ups in the metrics. So the approach that we followed is we rolled up the data at 10 minutes granularity for the real-time aspects. This was achieved by a Flink job. And Pinot's hyperlog column came into help very much over here. So hyperlog object, just to briefly explain, it's a probabilistic data structure which will allow you to do aggregations on unique count. So that's how we serve the real-time data. For the offline tables, we rolled up the data further with the hour and day level granularity. again, so we have a Spark job setup, which is doing the ingestion for the offline tables. So all in all, this helped us reduce storing so many events and then doing unique kind of aggregations across these events. We were having really good latency numbers. It was under 100 milliseconds for P99.5 queries. Yeah, so the setup was the 45 days of retention, 3 days of data in real-time tables, and the 45 days of data in the offline table. Moving to the second use case, this was about counting crashes or analytics around crashes. So if you see, each row over here does not represent a single crash, but it's a cluster of all the crashes. Each title is the representative of a cluster of crashes. So there's bunch of analytics around it. We show first seen, last seen, like first version where it occurred, how many users is it affecting, how many instances did we see in it, and how many devices does it affect. On the top, there are few more summary numbers. So if you see, the queries in this nature, in this kind of use case, are mostly group by queries, wherein you are grouping by the cluster of crashes and then providing aggregation of metrics for each group. This was kind of an easy thing for Pinot because this is what Pinot is built for, and we also did not face any challenge over here. So again, this was a hybrid setup because 45 days of retention was needed. We went ahead with all the basic indexes. So this table has like around 10 to 15 indexes set up because of the attributes the data has. Again, this is an active-active setup to provide more reliability. For querying, we serve data from both the regions, but in case of any disaster, we can always roll back to one of the active regions. This also helped reduce the ingestion lag for us. So in Elk, we were, let's say, in bad times when there was something bad happening in a mobile application and we see a crash spike, we used to see ingestion lag of few minutes, but now it's been under 10 seconds, and crash spikes are handled much more reliably in this case now. And overall, it has improved the UX also. We have seen page load improvements from under 1 second to under 3 milliseconds. And the next use case was around providing analytics on the complex data type. So as mentioned before, these are crash payloads. They can have a lot of metadata around it. There are network logs, analytic logs, and these are mostly nested JSON data structures. So usually Uber is 1 or 2 versions behind the open source's latest version. So if you are, so at least from 0.12 version onwards, there's a lot of optimization in Pinot that has happened. So for example, you can define which path of a JSON do you want to index. You can exclude paths in it. And there are a bunch of improvements around how do you query a complex JSON object. But at the time of onboarding this use case in Pinot, in Uber, we were still at 0.11. So we had to go with the approach of exploding this complex data into key value pairs, and then we were able to easily support these use cases. The thing with exploding is that you increase your data events that needs to be ingested. But our experiments and also the theory of Pinot say that it's very good at handling scale of ingestion. And that's also what we see over here. Yeah, but in the long term, we have a plan to move towards JSON index and utilize all the optimizations improved in the 0.12 version. Yeah. Another aspect is, I mentioned that crash payloads can have variable sizes, and then these can be large and very small payloads. So one of the challenges which we were facing is that how do we tune between the segment size and segment count? So Pinot offers you the capability to either define a row flush threshold, that is, after how many number of rows do you want to seal your segments, or you can define a size as well, that is after how much time you want to seal your segments. And then finally, there's a timeout threshold. That means that, let's say, after every 1 day, we want to seal a segment. So in this scenario, we did not go with the memory or the size-based flushing, but we went with the row-based flushing. That's mostly to restrict the number of segments that we are creating and restrict the number of segment commits that happen. Because what happens in a spike situation is that you'll see a lot of data, and if you're doing memory-based sealing, then you start committing too many segments in a short span of time. And that adds to ingestion lag. And the thing that we don't want is during any disaster happening, we do not want any ingestion lag, just to quantify the right, just to quantify what is the extent to which the application is not performing well. So we experimented with large segment sizes. The final approach that we adopted was that we'll try to keep the segment sizes under 1 GB, and based on that, we were able to come up with the row flush size. And in many cases, we were also seeing that up to 3 GBs of data is very easily, 3 GB of segment size is very easily supported through Pinot. One optimization that we did was we primarily banked on the fact that we should be doing peer downloads for segments, for sealed segment, instead of relying on the deep store, because in our case, the deep store is HDFS, and pulling data from HDFS usually timed out for the largest segments. Yeah. And one more optimization that we did was we compressed our payloads. So it was the application side of compression, and in Pinot side, there's a support for byte column. So that's how we were able to support it, Pinot. Yeah. And the final aspect was around text indexes. So since these are crash payloads and there can be error messages or the stack traces, there was a requirement of doing a lot of text searches. So we leveraged Lucene text indexes, which are there in Pinot. So what it helps in is it provides you the standard analyzer, which will basically tokenize your stack traces based on dot separators. So you easily get class name or module name based on which you can do filtering. There's also support for phrase text, so phrase match. So let's say a service is producing logs with some custom message, so users can come and search for their messages. So we felt that there is a need for more analyzers to be added in the Lucene indexes, and we've also created we have also taken up the task for adding this to Pinot. I've attached the link for it, so you can follow it if you want to. And then there were some issues, there were some minor bugs that we also encountered, and this is mostly because these segment sizes are often reaching their max size limit. So for example, in one scenario, we were seeing that our segments were not sealing because the index size was becoming more than 2 GBs. In terms of implementation, what it meant was the offsets were of type integer, and they could not store a number greater than the integer's max limit. So we bumped up the forward index writer version to version 3, which is also already there in Pinot. And this provides us the offsets of long type. And now we were able to seal the segments in which the indexes could be of size more than 2 GBs. There was also a race condition that we encountered in which our segments reported that they were healthy, but they were not consuming anything from the upstream. The bug was mostly around that the Kafka consumer thread was not getting spawned. It was being created from the constructor, and Java does not get. So it was being created from the constructor, and so it's very interesting. You can follow this bug. The thing is that there are certain limitations you can do inside the Java's constructor, and that's what the bug is solved. Yeah. And in the long term, we also plan to move some of the use cases to native text indexes, because at least in the mobile crashes, we see there's a lot of structured data, and with just minor massaging of the data, we can migrate all our use cases to native text indexes, which gives us very good cost benefits in terms of the amount of data stored and the amount and the time spent on querying the data. Yeah. To summarize our wins over here is, so we significantly reduced the mean time to detect whenever there was a disaster, because a disaster translates to spike in ingestion traffic. And spike in ingestion traffic was causing ingestion delays in Elasticsearch. And this is how Pinot is outshining Elasticsearch over here. So it's easily able to handle any kind of spikes in coming from Kafka side. And that's mostly because it avoids writing to a file and keeps everything in memory. We were having significant infra cost savings. We reduced our CPU cost from 80% by 80%. Our L cost, the previous setup cost has reduced by 70%. Our data footprint has reduced to 66%. So currently we are storing around just 50 terabytes of data. There's been a significant improvement in the UX, and the end users have also given a very good feedback on the UI. So there's a significant lower time for page loads. And then finally, it's all about reliability, which matters for tools like these. So better tolerance to spike, quicker lag recovery. So even if we see any kind of ingestion lag, which will be in just magnitude of minutes, so we were able to recover quickly from there. We also reduced the query timeouts. We were also able to reduce it. So in Elasticsearch, the technique which was being followed was that we were creating weekly indexes. So let's imagine that there was some disaster in mobile application, and because of that, the index size increased. So whenever you do a query which is touching that particular index, Elasticsearch usually used to timeout. But in case of Pinot segments, we are able to control the segment size instead of creating them based on time duration. So in this case, and then these are also better like the queries are better scattered and gathered over here. So that's how we had reduced the query timeouts as well. And there's another important thing that we were able to fix is that there was a lot of data misses that used to happen whenever we had increased ingestion throughput in Elk. But in terms of Pinot, we are seeing literally no data loss at this moment. Yeah. And in terms of learning, I think the biggest learning over here is we need to understand the use case very well before supporting. I think there should be a proper stakeholder, like we should manage the expectations between our stakeholders. So if you just go and look at the Pinot documentation, you might find this like a fancy thing that can do all the things, but it's you really need to understand the use case. For example, we were able to remove use cases like requirement for upserts because we were able to do some deduplication in the processing pipeline. We were able to identify what are the tier 0 use cases and tier 1 use cases. And based on that, we provided storage tiering. So for example, the most recent data has to be queried highly, like more frequently. So that's why we did storage tiering over here. So our offline tables are served from high IO machines, and our real-time tables are served from high CPU machines. And again, over here, Pinot has the configurability to use tag-based instance assignment in your tables. Second is that you cannot just let the use case owner team to write the queries. You also need to understand how they are writing the queries. And that's mostly to do with because people have in general relational background. So they try to solve things based on relational queries. But this is where we need to understand how we can like solve it in a manner that Pinot actually supports. So for example, there were requirements of join queries, which we were able to solve with subqueries. Then again, there was optimization with ID sets. So people were putting in static list of data for doing in-clause kind of queries. And we were able to solve it with, again, subqueries, which had ID set kind of optimization. Third is you need to tune the segments really well. So I'll say in most of the cases, like 90% of the Pinot use cases, you might not need it. But when you have a high scale problem, then you really need to look at your segment sizes and the segment count. So when we had higher or the larger side segments, we were seeing timeouts from the deep store whenever table restarts used to happen and the deep store copy needed to be downloaded. And when we had too many segments, then it was usually because too many commits were happening, and that was causing ingestion lags. So these were the things we found, and I felt that tuning segments is also an important learning over here. And then finally, there were issues around data skewness. So if your Kafka stream is not partitioned properly, you will, so if you look at Pinot's architecture, you have partitions created per, segments created per partition of Kafka. So if your data distribution is not even across all the partitions of Kafka, you'll also notice the data that is being stored in the hosts of Pinot, that will also be skewed. Problem with this is that some hosts can be overutilized very early and some will be underutilized. And you might run into a situation where you can have hosts going down. Second is so you can still have data distributed evenly across your machines, but internally data can be highly skewed during the query time. And it's because of some of the filters can lead to too many rows being scanned whenever you serve the queries. So in this case, what we did was we tried to focus on solving for the P99 and something which was which had to be solved. Like for example, the recent data matters most in terms of logging on logging kind of services, which is this one. So we made sure that if we can solve it by giving more timeout for the older queries which are least frequently used, then also it's a good solution. So that is what we did. In some cases, we increased the timeout for the queries because they were infrequently being done. And in most of the cases, the queries did not time out. Yeah, I think, yeah, these were the learnings from our side. Atri, do you want to add something?
Thank you, Rohit. Yeah, I think that's pretty much it. Rohit's done a great job of covering all the aspects that we had. And one thing I do want to highlight is that this was, again, a critical service, and we had no outages during this migration. So that was something that was a factor of both Pinot's reliability as well as our own preparedness in the overall migration. And yes, we have other use cases going on as well apart from this, which probably have a higher scale, and we have been seeing consistent improvement areas in terms of what Pinot can do better, for example, with table rebalancing and upserts in general. So I think as the migration, I think I've seen more use cases here where people are moving from Elasticsearch to Pinot. So this overall journey where people are moving from a full text search, which is kind of also analytical engine, to a true time series analytical system, I think Pinot will definitely improve. There are many other areas of improvement that we probably would not, we as in the Pinot community would not have thought of before. But with such use cases coming in, I think the evolution of Pinot is guaranteed. So yeah, um, I think I'm personally very excited about this, both as somebody who's involved in the overall migration and also as a Pinot community member. And we should be exchanging notes across this with other team members. So yeah, thank you, Rohit. I think that's it from our side. We would love to take any questions.